Good morning, everybody. Today we start physics, and what we're going to be talking about in this particular physics unit is light. So where does light come from? How does light behave? How do we see light? That kind of thing. So just to let you know, we're skipping ahead and our textbook section starts at chapter 10. Okay, so your textbook references will be from chapter 10, 11, and 12 for this particular unit. So we'll start off in chapter 10. We know that light is a form of energy. And the way that light travels, it travels and behaves as a wave. When you continue on in physics, this is kind of a huge deal. So there's the particle wave theory of light, and I'm going to let your physics teachers teach you that. But waves are an important thing, and we're going to talk a little bit about what a wave is in really soon, actually, like in a couple of minutes. But before we get there, let's talk about how fast light is. So when they say the speed of light, he's faster than the speed of light, they're actually saying something that can actually happen because light is the fastest entity we know. Okay, and the speed of light is 300 million meters per second. So an easier way for us to write 300 meters is to use this form called scientific notation. And I'm sure you've seen this somewhere in math maybe, or in other science classes. So what all it means to use scientific notation, and the reason I'm saying this is because it makes your math a little bit easier, is when you're dealing with your very large or very small number, you know that your decimal in the large numbers, greater than 1, is at the end of our number. Okay, we don't necessarily write it, but then we move our decimal place 8 times to the left, and we end up getting 3.0. And the fact that I moved it 8 times to the left means that represents 10 to the power 8. So 300 million can also be written as 3.0 times 10 to the power 8 meters per second. Okay. This will be the main number that we're dealing with in this particular unit. So it's something that we usually expect you to know. Okay, it's not usually given to you. So when we talk about light, light is the fastest moving thing that we know about. And the speed of light, 3.0 times 10 to the power 8 meters per second. But energy is also like light, and it also moves in waves. Okay? Some kinds of energy need something to move in, okay? And that's something that it needs to move in is called a medium. So we're not talking about the size of your t-shirt. We're talking about what light or energy can travel in. Some types of energy don't need a medium to travel through, okay? And radiation is one of those things. So sometimes you feel heat radiating off of a fire. That radiation means that it doesn't necessarily require a medium. So when we talk about a thing called an electromagnetic wave, it's a wave that has electric qualities and magnetic qualities. It doesn't need anything to travel in. So it doesn't need a medium, so it can travel in a vacuum. Okay? And for instance, like in space. It also travels at the speed of light, which is what? 3.0 times 10 to the power 8 meters per second. So let's take a look at what waves are. Now, you would have seen waves a long time ago, and the reason I know this is because I just had to help my daughter in grade 4 learn about waves. But if you don't remember all the way back to grade 4, let's revisit, shall we? Okay, so there's 3 characteristics with a wave. Speed, wavelength, and frequency. So when we're talking about light waves specifically, okay, the speed is the same. This is not always the case for every kind of wave, but since this is our unit of light, let's just deal with light, okay? So light travels at that special number, 3.0 times 10 to the power 8 meters per second. Then we have wavelength. And wavelength let me just refer you to this diagram right here. What a wavelength is it's the distance between two crests, which are the top part of the wavelength, or conversely, two troughs, so two bottom parts. And so that's what the wavelength is. Now, I'm going to use this symbol because I prefer to write less. The wavelength is referred to this symbol called the lambda symbol, okay? And it's measured in nanometers, okay? So not like the speed of light in meters. Nanometers are pretty small. They're 10 to the power negative 9 meters, okay? So when we talk about wavelengths, we're talking about things that are pretty small. Lastly, the frequency. So if we think about frequency, we think about how often does something happen, right? Like Mondays have a frequency of 1 in every 7 days, okay? When I talk about the frequency of a wavelength, it means how many waves can happen in 1 second, okay? So the longer the wavelength, the less frequency. The shorter the wavelength, the more frequency, okay? Because if it's shorter, more wavelengths can happen in a second. The other thing that we need to consider is that frequency measures the energy of a wave, which kind of makes sense because you know that you can kind of correlate how fast something is with how much kinetic energy there is. So the greater frequency, the faster that wave is moving because it's shorter, and because it's shorter, it has more energy. The slower a wave is moving, the longer the wavelength, the less frequency, the less energy. We can say these things are directly related, okay, if you want to put a mathy spin on things. So a light wave has a maximum and minimum value. So when I talk about that, here's my max value, the crest. Here's my min value, the trough, okay? And the height of this wave, so as you can see, it's right here, the amplitude, illustrates how high up the crest or the trough is. And that amplitude dictates how bright the wave is, okay? And the wavelength determines the color of light we see. So think about it this way. There's a characteristic wavelength that tells us the color, but then the height of the crest or the trough tells you how bright that light is, okay? So let's just take a look here. When we take a look at our wavelengths, this is an indicative of a short wavelength with high frequency. Because it's short, like I said before, many waves can pass by within 1 second, pass by a certain point. And so in this case, these guys will have higher energy. Okay? When the wavelength is longer, it takes more time to pass, so fewer wavelengths will pass through a point within 1 second. So it's got low frequency, and for that reason, it has lower energy. Okay? So now, when we take a look at how we're going to use this information about waves, well, it has to do with the colors we see, which we already know are because of wavelength. And it has to do with how those things hit our eyes and how light is related to all of this. So there's a very important spectrum called the electromagnetic spectrum. And we already talked about electromagnetic waves. So they have an electrical field and a magnetic field. They don't need to travel through a medium. Okay, they don't need a medium to be able to travel. They can travel through a vacuum. Okay, so if we take a look at what this diagram is showing us, what we're seeing here are short waves, high frequency, and long waves. And some of these things might be very familiar to you, but the one I really want to focus on, and it's kind of the one that we're relating to the whole unit, is the visible spectrum. Okay, and it is, I won't say in the middle, it's a little bit towards the shorter end of the spectrum, but this represents the light that our eyes are able to detect. Okay, so you'll see that radio waves are longer. Gamma rays are the shortest rays on this electromagnetic spectrum. Okay, so these are the ones that can actually penetrate into your cells and damage DNA. X-rays are also pretty short, and they can also, because they're so, they've got such high frequency and short wavelengths, they too can penetrate skin. That's why when you go to the dentist's office, you have to wear that lead covering over your reproductive organs, usually your torso, because we know that when you're getting an x-ray done on your teeth, that those x-rays can penetrate cells and damage DNA. Okay, but we are not going to worry too much about that right now. We're going to worry about this thing called the visible spectrum. And when you look at the visible spectrum, or when you actually consider, not look at it, when you consider the visible spectrum, we're going to be talking about white light, because most of our light comes at us with one color. Okay, but if we take that white light, and I'm just going to scooch this up, and we put that white light through a prism, so it's usually a glass or a Pyrex prism, we can actually separate that white light into a rainbow. And that rainbow, and I don't know if you remember this from your youth, but we can separate the colors of light into these basic colors. Now, that's not saying that's every color that we know about, but these are the colors that white light can be separated into. So I learned it as Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. Okay, and what you're going to see is that these 7 main colors behave a certain way. So let's take a look. Violet is on this end of the spectrum. And remember what we said before, different wavelengths give off different colors. So if we take a look at this end of the spectrum, this would be the shortest wavelength. Okay, and that's why it looks like violet. All right, and when we see that, who is the violet next to? Ultraviolet. We can't see ultraviolet light. That's the light coming from the sun. Okay, we can see violet. And as you can see, the violet and the ultraviolet is on the shorter end of the electromagnetic scale, but the shortest wavelength has the highest frequency and also the highest energy. Okay, this is why some forms of ultraviolet light can pigment your skin, can cause skin cancer, because they're at higher energy. Then on the other end of the spectrum, red is right next to infrared. This guy has a longer wavelength, right? So because he's longer, he's moving slower, so there's less frequency of the wave and therefore lower energy. And on the other side of the red is infrared. You may or may not know what infrared is. Infrared detects heat. So sometimes there's infrared sensors on like motion detectors to see whether there's people in the dark. So a lot of military applications for that. Okay, they can do heat sensors. We don't see the heat radiating off of people's bodies, but there are sensors for that. Okay, so when we talk about visible light, this is what we see. My Roy G. Biv, my red has the longest wavelength, least amount of energy because it's got the lowest frequency. My violet is the smallest wavelength, so it's moving the fastest and it has the highest amount of energy. And this is a great little video. Okay, So there's that. I'm going to continue with the next lesson on a different video. So stay tuned.